Okay, yeah, thanks for having me here. This is the plan of my talk, but before, let's appreciate the room. I think if I researched this right, this is from the 14th century, 1393. It's a church from the monastery. I think I've never lectured in a room that old. So while the setup is not perfect for math, okay, it's great to be here and to speak in this room, gives a series of lectures. Before I give a rundown of the plan for the week, you may want to take a photo from the last line and work on it. That's the best way I could come up with in sharing these slides. So the problem with these non-Blackboard talks, of course, for me at least, is you can't leave back unless you take notes, and taking notes is too slow, okay? So this is the slides that are coming up just on some file sharing service that I randomly introduced, and the link came out like this. I apologize. If you have a better method to share some file, let me know, and we'll do this for the next talks. Okay, so the plan for a talk is this about logarithmic Gromov-Witten invariants. I don't assume that you all know what log geometry is. So I'll start with some geometric introduction to logarithmic geometry that hopefully, even if you're not interested in logarithmic Gromov-Witten invariants, might be useful in some other context in the future. Geometric means I'll work over the complex number field and try to emphasize the geometry, but log geometry is also interesting in arithmetic contexts. So that talk will likely spill over a little bit into tomorrow, so that's why I put a Monday, Tuesday, and then I'll talk about tropicalization and log smooth curves, still no target spaces. So the story is that logarithmic geometry naturally has a tropicalization functor. So tropicalization is kind of, or tropical geometry is built into log geometry, if you want, okay? And this is how this comes up in this context. And we'll see how log smooth curves becomes like length graphs and so on. And then we finally, on Wednesday, spilling into Thursday, probably we talk about logarithmic Gromov-Witten invariants. And I'll introduce the technique of Artin fans, hopefully again useful also in other contexts. And I'll introduce this variant on logarithmic Gromov-Witten invariants involving negative contact orders called punctured Gromov-Witten invariants. Then Thursday is a slightly technical thing, and I might just not have time to get into it, okay? So I would love to. It's a little technical, but it's very cool. And you'll see how everything plays together. And but if I don't get to it, it's not a huge loss. I definitely want to come to the application on Friday, which was the main motivation for Mark Rose and me to get into the whole story, which is intrinsic mirror symmetry. So that involves punctured Gromov-Witten invariants. So the whole thing has been developed, and the gluing formula is in place and nicely, and it gives us a way to produce mirrors without any ad hoc choices for situations that are interesting, that coming out of birational geometry. Okay, so if you are an honest algebraic geometer, you don't like ad hoc constructions like start with a toric variety and take a hypersurface. Okay, you want to have something like, okay, I want to have a logarithmic Calabi-Yau, which is classification theoretically like this, Kodaira number 0, and so on. Yeah? So this is what, and we have a mirror construction for that, which works and hopefully obeys homological mirror symmetry and enumerative mirror symmetry. Okay, so I'll come to the first slide. Is that legible to everybody? Size fine? Can I go a little slower, a little smaller like this? It's fine still. A little bigger. So you think I should do this thing that you suggested? Oops. Yeah. Okay. Okay. For those people like me who are almost blind. Okay. So first to get things straight. So what I'm talking about, I'll mostly talk in the algebraic categories, so algebraic varieties, schemes. And it also works with a slight variation of what I'm saying with algebraic stacks. But you could also, the whole thing also makes sense complex analytically if that's your game. and then you would have analytic stacks. But I would want to work over the complex numbers, although anything works over an algebraically closed field of characterization, no change. But it also, some also works for other things. Okay, anyway. So let me motivate what log geometry is. I've talked about log geometry for like more than half of my career. And it has been a disaster at first, and then became kind of okay. And by now, I think I've optimized the ways I have to present it. It's still not always super smooth. But anyway, let's see how it goes. So I think the best motivation for log geometry you look at normal crossing varieties first. So let's call it a simple normal crossings variety. So you would take some open subset, or maybe algebraic geometrically, you really want to work in at least the smooth topology or the étale topology. So this arrow up here this might just be an étale map. So in any case, you take an open object in your X, and you have a smooth map to AR. And the divisor that you take and want to define to be normal crossings is a pre-image of the coordinate, union of coordinate hyperplanes in IR. Okay, so this immediately applies that we want that D intersected U is a union of a bunch of components. And simple normal crossings says that the DIs kind of close up to smooth divisors in globally. And generally, you might have self-intersections, like for this nodal cubic, where you see try to draw a 2-to-1 map, an étale 2-to-1 map for this nodal cubic, to show you how this is still a normal crossings, how this still fulfills the definition I gave. In any case, so if you have these simple normal crossings, let's take simple normal crossings. Okay, normal crossings is a slight variation. Let's not make our life too complicated. Then X comes with a bunch of line bundles Li, one for each divisor. So you would write this as OX of Di if you write the sheaf, and the Di would be the zero locus of this canonical section Si. Okay, so let's call this Li maybe. That's the sheaf of regular sections of this line bundle. And then you have the canonical section Si. So this is, you could view as a morphism from OX to OX of Di. You also know that if you restrict this sheaf to Di, then you get the sheaf of sections of the normal bundle, which differentiate geometrically is really the quotient of the tangent bundle by the restriction of the tangent bundle of the ambient space by the tangent bundle of the divisor. Logarithmic geometry would look at the dual inclusion, okay? So you look at, that's of course, this data here is of course equivalent to the dual information, so the inclusion of the ideal sheaf OX minus Di and OX. Now so if you look in classical literature, you get all these iterations. So you can take Di intersected Dj, or D intersected Di is a normal crossings divisor on Di. So it has the same structure, okay? And it has normal bundles. And the normal bundle of Di intersected Dj on Di is the same as the normal bundle of Di in X restricted to Di. And you get all these orbital formulas, okay? So you can compute it in terms of the normal bundles, it's a tensor product, and so on. Okay, it's a bit of a mess. And all of this kind of information that you find here is contained in this log structure. And that is simply the inclusion of the sheaf of functions, regular functions that have zeros only at most on D. Okay, so it's an invertible function away from D. And I've written it slightly sloppily, right? You would have to push forward to make it a subsheaf of OX, but I think it's better readable like this. So it takes a sheaf of functions that are regular functions that are invertible outside D, and takes inclusion into OX. Now, this is, of course, not a coherent sheaf or even an OX module. You lose the addition operation, but you can still multiply. So this is a sheaf of multiplicative monoids, and that makes logarithmic geometry so kind of head-scratching because we are so used to working with coherent sheaf, and some things just go wrong. But it's not, you have a slight, small learning curve, but it's not horrible, okay? Okay, so you can multiply. And that thing here is called a log structure. So any pair from X with a normal crossings, smooth X with a normal crossings divisor comes with a log structure. Now, at this point, it's just a different language for things that you can always write down very classically. Okay? No need to ever use the word log. But let's look at what this looks like, get some first impression. So let's look at the affine plane with coordinates z and w. Then the stalk of this sheaf that I just wrote down, let me pull it down again, is away from these coordinate axes, of course, just the invertible functions. Okay, so no zeros. Then if you go to a general point on one of these axes, you have one order of vanishing, so you can write any section here, any germ of section, as a power of the coordinate with zero, this coordinate axis. So the w, a power b that has a vanishing order times an invertible function. So it looks like it's isomorphic to n cross O star. And the well, this is slightly strange, right? So here it's additive, here it's multiplicative. And similarly symmetrically here, of course, and then at the origin you have two vanishing orders, A and B, and you can write it as Z to A times W to B times H, so it has an n squared cross O star. Okay? So then there's a sheaf of an associated abelian sheaf, MX group. That's sometimes a little easier to talk about. And most importantly, you have a discrete part, which captures these exponents here, the A and B that I have, which you get by dividing out, multiplicative this kind of submonoid sheaf, OX crosses, the invertible functions. And you could just keep the discrete part, the vanishing orders. If you have a simple normal crossings divisor, that sheaf is very easy to write down, right? It's a copy of the natural numbers for each di, and then you take the direct sum. Okay? An MX bar group is a corresponding constructible abelian sheaf where this n becomes a z. Okay, so this looks like an n here, an n squared here, and 0 outside. That's a constructible sheaf. How do we get these line bundles that I mentioned earlier, this OX di, or maybe the OX minus di? So the global sections in this case, in the simple normal crossings case, is just the Z to R of the MX bar group, okay? It's a Z to R, which gives you these vanishing orders along the divisors D1 to dr. So you get A1 to AR are integers, and you have this quotient map from MX group to MX bar group dividing out OX star, which takes this kind of regular function with zeros at most along D, and takes the orders of vanishing along each of the di's. Okay, so that gives an R tuple of integers. Now, if you fix one tuple, A1 to AR here, and take the pre-image, that is a torsor on an OX star. Okay, that's just how it is designed. How it is defined, you just keep the H, and the H acts simply transitively on all these things. So this pre-image, maybe the T should be has some index A1 to AR, is an OX star torsor. And an OX star torsor has an associated invertible OX module that you get by taking the direct sum with OX and dividing out OX star. And I keep forgetting if it's diagonally or anti-diagonally. That depends. You would get the line bundle or its inverse, okay? So doing it correctly, you get exactly this ideal sheaf OX minus some AI di that I mentioned before. You should interrupt me if anything becomes unclear, okay, or you are losing track and so on. So far, everything okay, I guess? Okay.
Can you go back to the example?
Yep. Sorry, I can't see you. Where? Over here. Yes. Say again. X is A2. Yeah, so it's a simple, so it's a smooth variety. The divisor is the union of coordinate axes. Yeah? Okay. And the sheaf lives everywhere. You know, the sheaf is everywhere. but is kind of boring outside of these coordinate axes. It's just an OX star, but then has some interesting kind of twists along the DIs, along the Ds. Okay, so the next thing is, so the next thing you need, next ingredient for talking about log geometry is toric geometries. You need to know a little bit about toric geometry. So I'll give you a minimal rundown that will be pretty quick. Let me just so who's familiar with toric geometry? Okay, so it's like half. So it's good. Stop me if I'm going too fast. Fall asleep, or do something else if it's too boring, okay, and then I'll try to read the room and adapt my speed, okay? So this is some basic toric geometry. Toric geometry is about, let's say it's about finitely generated affine toric geometry. It's about finitely generated monads. So these are all submonads of a Z to N, okay? You just take some numbers in Z to N, some elements of Z to N, and take the monad additively generated by it, okay? So monad has a unit, that's a 0, and then you can add, but you may not have inverses. Okay, so that gives some finitely generated monad. So you can write it set theoretically like this. You take multiples, positive integral multiples of each of your generators M1 to MS. And the one that is most popular in toric geometry takes a cone that I write here sigma dual, so it's rational polyhedral cone, and you intersect it with Z to N. Rational polyhedral means it's generated by finitely many, or defined by finitely many hyperplanes. Okay. Why does one write sigma dual? Well, that's the simple reason is that you want to make this full dimensional, and you will get this when sigma is actually strictly convex, or strongly convex. I never keep in mind what, I think it's called strongly convex. A strongly convex rational polyhedral cone, meaning it doesn't contain a line. Okay, so it's a sharp cone. And whenever you have such a cone, then the sigma dual is full dimensional, but that's the only reason. So sigma is a rational polyhedral cone if and only if sigma dual is, okay, but the dimensions may vary. In any case, whenever this rational polyhedral, there's a simple theorem called Gordon's lemma that tells you that this is finitely generated. And so then you can build an algebra from this P that I write CP, the monad algebra, similar to the group algebra that you would obtain when P is a group. So you take finite linear combinations of some dummy variable chi with exponents in this algebra, in this monad P. So quite explicitly, you could write this as chi1 to m1, chi-n to mn, if your monads, a P is a finitely generated submonad of Z to N. So then you get a bunch of exponents that you can play with, and it becomes a subring, a finitely generated C subalgebra of the Laurent polynomial ring generated by x1 to xn to plus minus 1. That would then, in this new notation, CP would be written CM, where M is a kind of more intrinsic notation for Zn. It's always important to use M and N to capture the correct functorial behavior. So N is a dual group to M, a dual lattice. Okay. Of course, you know how to turn a finitely generated C algebra how to write it as a quotient of a polynomial ring. So that depends on choosing generators. There may not be a minimal choice, but you choose these generators, and then you get a surjection from this polynomial ring to CP that maps UI to chi to mi, and exhibits your CP as a polynomial, as a quotient of a polynomial ring. And then, of course, you get an embedding of the spectrum of this CP into an A to S, where S was the number of generators. You know, I had M1 to MS. One can actually compute this. So yeah, there are programs that would do that. So you give me M1 to Mn, and I'll tell you what the phi is. It's a toric ideal. Toric ideal means it's generated by binomials, and the binomials are of the form u1 to a1 to us to as minus u1 to b1 to us to bs. Whenever you have this relation, this is a relation in in P. Okay, you can't write the minus or a quotient or something, right? That doesn't work. But you can write this equation makes sense in this monoid. Okay, so that can be computed in any case. I'll just write this down because we'll do some examples. And then you may wonder, when do you get P's that are of the form sigma dual intersected z to n? So the sigma would be what I could call, write P dual. Actually, that conflicts with some notation I'm doing later. So let me write this P dual OR, which is the harms as monoids, okay? So this is a harm of monoids from P to the additive monoid r larger or equal 0. It's a dual cone. So when is it the case? That is the case. So this is always true, right? It's always a subalgebra of this, a submonoid, sorry, of sigma dual intersected Cn. It's an equality if and only if P is a monoid that's called saturated. This means that if a multiple of some element of Zn, so a dm is in P, then m is already in P. So if you think of this cone and the integral points in there are no holes. Okay, you can fill in holes. That's saturated. And we will always, in this talk about saturated. Not quite true for the punctured things, but okay. Almost always, okay? So let's do an explicit example. So let's take sigma the cone that is generated by 0, 1 and k, 1, and then of course you need as a cone, but as a monoid you would need more integers here. But it's this kind of region that I shaded. So this is a picture in NR. In the dual thing, so the perp of 0, 1 is 1, 0. The perp of k1 is minus 1k. And then you get the signs right, and you see the dual cone is this region here. So the P would be the integral points in this region. So as a monoid, it is not enough to take 1, 0 and minus 1k. That doesn't generate all the integral lattice points in there. You need one more, which is 0, 1. How do you check? You take the determinant of 0, 1, 1, 0, that's 1, and 0, 1 minus 1k is also 1. So these form lattice spaces. And of course, once you have a lattice basis in a cone, it generates all the integral points. Okay? So this is a generator of the monoid. This means that the algebra is of the form, is isomorphic to the familiar polynomial algebra ZWT with one relation ZW equals T to K. If I call the Z this guy, the W this guy, and the T this guy. Okay, I wrote it here. So you see how this relation comes up. Z times W means you have to sum the exponents 1, 0 and minus 1k. This gives 0k, which is k times 0, 1. That translates into this multiplicative equation ZW equals T to K. Okay? So if k equal 1, so this is a very, very important example for everything that's coming. So this is essentially what log smooth curves look like locally. Okay? Once you understand this example, it's very important. For k equal 1, you get what we already kind of did, namely the total space is you can eliminate t, right? You get a polynomial ring A2 where C is ZW, and then I have a normal crossings total space. I mean, a smooth total space with a normal crossings ZW equals 0, and this map to ZW to Z times W would exhibit this A2. It's a fibration by curves over an affine line. The central fiber is the union of two copies of A1. The general fiber is a C star on GM. Okay, so you could view this as a semi-stable degeneration of C star to two copies of C. Actually, that's true for all k, but for k larger than 1, you would have to base change this picture by T to K. producing an AK minus 1 singularity in the total space at this point. That you see here, right? That's a two-dimensional AK minus 1 singularity. Okay, so let's do something more interesting. That is still all normal crossings. Let's see why log geometry gives us more flexibility and has maybe better properties than just talking about normal crossings and smooth spaces. So if I take sigma dual, the cone over the square, the standard square, so these are the integral points of the standard square, or explicitly, I've written it like here. Yes, oops, there's several typos. Oh, sorry, no, that's correct. Sorry, this is this is a cone explicitly. The dual is actually isomorphic to the cone, but it's hard to see when you dualize, okay? Hopefully I didn't do the computation wrongly, but the dual looks like this. We don't need it here. In any case, we want to take sigma dual and then take the integral points. And you see, this looks like this, okay? I've tried to kind of draw this. Here's your square. I take the cone over it, meaning I put the square in height 1, and then take the cone generated by the square. And you see these kind of extremal points here, x, z, y, w, and they actually generate the monoid. That's not hard to see. But there's one relation, namely, if you take x times y, you would get the same as z times w. You see it here, right? This plus, where is it? Plus this is z plus that. Okay, that gives this one relation, and that is this quadric cone in dimension 3. And it's also a CT algebra, so you can also view it as a degeneration by mapping T to xy or zw, and you can write it as a tensor product of C of xy tensor of C of zw over CT. Now, each of these is the same as what we did before here, right? But you see the fiber product of these two things is not normal crossings anymore. And it's I mean, it has nothing to do with normal crossing varieties, right? It's what could be called toroidal crossings. The total space is the toric variety, and the morphism is a toric morphism, and that is what you will get in logarithmic geometry as well. Okay, so this is what I said here, what I wrote here. So this gives us degeneration, and this is a degeneration of C star squared to 4 copies of A2. And to picture this, I like to flatten it. So it looks like this. It looks like a fan, but this is really a geometric picture. So you have these 4 coordinates axis, and here you have 4 copies of A2. And they fit together in this kind of schematic way. So each two copies of A2 either meet in a point, or they meet along an A1. Okay, and they have this cyclic pattern. Okay. So where's the torus? So why is this all called toric geometry and so on? On all these pictures, whenever you have a sigma dual intersected M, or any submonad of Z to N for that matter, you get a torus action because you have a graded subalgebra of Cm. Cm is M graded, and whenever you have an M grading, it gives you a torus action for the spec C of M. Spec C of M is this torus, so geometrically C star to N, and it acts on the spec Cp, which I now write as TV sigma for toric variety associated to the cone sigma. So there's a GM to N acting on it, and of course it keeps all this pattern that I drew before. So for example, it will map D1 to itself. It will map this kind of coordinate axis, this A1 to itself. It will fix this point, and so on. So these toric varieties have these, and that is actually the definition of a toric variety. Let's ignore the normal first, okay? So for purists of toric geometries, they would say a toric variety is a GM to N equivariant partial compactification of GM to N. Okay, partial compactification would have to be made precise. It means you have a GM to N in your variety, and it's a dense open subset. Okay. And then you automatically get a toric divisor, which is a complement of this guy, and it's always a divisor. Okay, the complement of this thing here, of the torus, which is embedded in there, is this divisor. I should alert you that a toric variety is not just a space with a kind of dense torus orbit. You also have a distinguished point. It's sometimes very important. So you have the unit of GM to n is part of the data. Otherwise, everything goes pear-shaped. Okay. So this part of the toric divisor, toric variety. Then quite often you ask these to be normal. Actually, I should remove it here because I have this parenthetical remark. So you often ask this to be a normal toric variety, and if you are in the affine case, that is equivalent to saying that your monoid is saturated. So it's of the form sigma dual intersected M, as said before. I missed to say this. So the toric divisor, there's one irreducible component of the toric divisor for any ray of this sigma. So going back, here we had one, sorry, this is sigma dual, but sigma looks the same, yeah? So sigma also is this kind of cone over a square, but it's kind of tilted. And you have these 4 rays here, and these are in one correspondence with the irreducible components of the divisor, okay? So it's not hard to figure out. You look up, you think about it yourself or find any book and it will be explained. Yep, go ahead. It's not a what?
It's not just a stable divisor. It's really
this is equivalent. So any divisor that is GM to n invariant will be of this form, will be a union of these components. Yeah, because it's contained in D, right? And and these are the irreducible. These are sometimes called toric prime divisors. I didn't write it. Okay, so there's an alternative construction. How am I doing time-wise? I might just skip it. Sorry? On page 5. Oh, I think that's fine. I can give the construction. Yeah, I like that because in most books, this is not written really intrinsically, but you have, and you wonder which side you are on. So let me give you how to write this correctly. So there's a quotient construction of toric varieties, GIT construction if you want. So I just do the affine case. There's no GIT. It's just invariant rings. And it's due to David Cox. So these are called Cox rings. The first appearance of Cox rings. Cox rings also appear in a wider context. So let me write n as z to n, and we have this cone sigma, and sigma of 1 is a set of rays. Well, I should say right away. So from now on, all my toric varieties will be normal. Okay? Or maybe I should say, what is a typical non-normal thing here? How would you get a non-normal thing? I said something about saturation. Did I miss to say this? I see here, right? So what is a typical non-saturated monoid? You take the natural numbers and take in there the monoid generated by 2 and 3. Okay, so this is missing the 1. So the saturation would also contain the 1, and then you get the natural numbers that gives the affine line. If you take the spectrum of this, you get Niel's parabola, right? You have the equation x squared equals y cubed. If this guy is an x, this guy is a y. Sorry, if this is an x, this is a y, you get the equation x squared equals y cubed, and you get Niel's parabola. So that we don't do that, okay? So from now on, all toric varieties will be normal. Okay, so I had the quote. So the Cox construction. So this is an alternative construction of normal toric varieties. So it takes a set of rays. Let me call sigma 1. The rays are rho 1 to rho r. And then the Cox string starts from this guy. So you take map sigma of 1 to n, which of course is canonically the same as sigma of 1, z to n to sigma 1 or something, right? But let me call this chi1 to chi-r. So if I chose a numbering rho 1 to rho r, so the chi-I are chi to ei. And, but the ei would be an element of the dual. So ei would map rho j, this element of sigma 1 to 1, to delta ij. So ei of rho I would be 1, and ei of rho j for j not equal to I is 0. Okay, so this is a ring. It's of course just a polynomial ring. And then there is an interesting grading that kind of captures these rays, the coordinates of the rays. And it's intrinsically written as follows. So you have a map from hom nz to map sigma of 1z that comes from the embedding of sigma of 1 to n that maps rho I to rho I, okay? So this dual map would then map rho I to m comma ni, where ni is the primitive, sorry, no, everything is written. When I write rho I, so when ni is a primitive generator of rho I. So rho I is a half line, okay? It has integral points, and there's a primitive integral point, so smallest integral points, that's my ni, and this would be the map, okay? So in any case, there's this canonical map from M, the dual lattice, to this kind of guy. So this is a z, explicitly in coordinates, that's a zn, that's a zr. That's how you find it in books, okay? They just write down this matrix. And you grade this R, this ring, by the quotient. So by the quotient of this, by the quotient homomorphism from map sigma of 1z to gamma, to map sigma 1z mod m. So that grades R, and this grading defines an action of spec C gamma, but C gamma, that's subjective if you assume that sigma is full dimensional, okay? I didn't write it. I assume that sigma is full dimensional, then this will be subjective, and you get an R minus n dimensional lattice, gamma, and the spec C gamma is then an R minus n dimensional torus that acts on this AR. And the categorical quotient is just the invariant subring given, the categorical quotient is given as spec R gamma, where gamma is the invariant subring under this grading or under this action. Okay, so that's the degree 0 subring, and and then the fact is that this R gamma is another way to produce your monoid algebra CP. Okay, so that gives a quotient construction that you sometimes find in the literature, and especially physicists love this kind of construction. So most of the time you see a toric variety in physics, that's what they will do. Okay, so we have seen that an affine toric variety, I have now 3 ways to write this, or 3 notations for it. I write it as TV sigma, as spec CP, or as this quotient AR mod GM. Actually, I should do a categorical quotient, GM to R minus N. Okay, so what does this, so this is what I wanted to say about toric geometry, okay? So now whoever knows this very well can wake up again. So toric log structures. So toric geometries come with log structures, and that is simply because much as my initial example of a normal crossings variety, it comes with a pair of a space with a divisor, x comma d. And whenever you have that, you can write down something very similar to what I wrote down in the beginning. Where is it? This thing here. I can take the regular functions that have zeros at most along the divisor. And that will give the toric log structure. So I just do it in the affine case. If you know how to globalize affine toric varieties by using fans, you will know immediately how to globalize this. Otherwise, it won't help much to say this in 5 minutes. So you take, we generalize this construction from before, And we obtain this O star x minus d intersected OX inclusion into OX. And that defines a log structure. It has a discrete part, mx bar. Oops, there's a star missing. And now okay, so now we have this, we still have maybe R components, order D1 to dr. Actually, I had S, right? Did I have S rings? No, I had, this was still R, yeah. I still had R, okay, that's fine. Okay, so now, what do I get? So now, the problem is that on a toric variety, not any linear combination of the di's is Cartier. So there wouldn't be a function having exactly that order of zeros. Okay, so if you take regular functions with zeros at most along di and look at the orders of zeros, you won't get all n to r. You just get a subset. It's a submonad. It is saturated in this case, okay? But you get an image, and the image is isomorphic to the set of, or the monad of, actually effective, I should say effective, principal Cartier divisors supported on D. Okay, so that's some submonad, saturated submonad of Z to R. So for example, for this case where I had the cone, where sigma dual was a cone over a square, we had 4 divisors, D1 to D4, okay? These were in this planar shape that looked like the fan of P1 cross P1. And then as some AIDR is Cartier if and only if the coefficient A1 plus A3 is equal to A2 plus A4. Okay, so for example, each individual AI is not Cartier. DI is not Cartier. Okay, so now we have normal crossings log structures and we have toroidal log structures, but still, it's just a space of a pair, toroidal pair, and people have done that, toroidal geometry. If you look in the book of, Kempf-Knudsen's Mumford Saint-Donat from 1971, Springer lecture notes on toroidal embeddings, where the notion of a toric variety was introduced, you will find that. Okay, so they talk about toroidal pairs, and you will find a lot of stuff on this geometry. So log geometry makes this a lot more functorial and flexible to work with. So that requires the notion of an abstract log structure. So an abstract log structure is a morphism, mx to ox, of sheaves of monoids. Okay, so this is a sheaf of monoids, where this is multiplicative. And you want that the pre-image of the invertible functions, that's a submonoid of mx, maps isomorphically under alpha to ox star. Okay, so this looks awful, but you can immediately see that what we did before fulfills that condition, right? So a function that has no zero, a regular function that has no zero along the D, that has no zero away from DI and none on DI, has no zeros at all, right? So that is an OX star. So that will be an example of an abstract log structure. And in general, you have this definition. So that's a log space. But the good news is you won't need to understand much more than toric log structures. And the following construction I will give you in a few seconds. But before doing that, let me tell you what else we get. So you also get this discrete part. You can always do that. Mx mod OX star, you get an mx bar. Some discrete part. It may not, from this definition, it may actually not be discrete. Okay, let's be honest. But for all the applications I'm doing, it will be discrete. And you have this quotient morphism mx to mx bar. So this means that whenever you have a section on an open subset of mx bar, you get a torsor by taking an OU star torsor by taking the pre-image under the kappa morphism, and an associated line bundle, which kind of, where this set theoretically embeds as the sheaf of sections without zeros. I'm not giving you the alternative point of view. You can read it if you like. Actually, it might be fitting because it's due to Vistoli, just a few blocks down. Angelo Vistoli, who wrote it in a paper with Born, parabolic sheaves, and Mattia can tell you more about it, of course. So that's a cool way to also think about it. But so I promise that you won't need to understand much more than toric log structures by this construction. But before doing that, let me do one more thing, which are log points. So log points, that's kind of interesting log geometry. You have interesting structures on points, even if you're not talking about non-closed fields and stuff, right? We are on C algebras, a point is just spec C, period. Here, you take a monoid with trivial invertibles. That's called a sharp monoid. Okay, I think of this as an additive monoid. And then one writes spec Q to C. So Q to C is a map, I didn't write it. So Q to C is the only map one can really meaningfully write down. It maps 0 to 1. That looks strange. 0 is the additive unit in Q, and 1 is the unit in C as a multiplicative monoid. Okay, so unit maps to unit, I have no choice. And everything else maps to 0. Okay, and you take spec Q to C as a notation means you take spec C, so that's a point as a scheme, and you take the monoid, which is then a monoid sheaf on this one point space that looks like Q direct sum C star. And I take C star multiplicative, Q additive. Looks strange. You will see that it's totally natural in a few seconds. So now comes the pullback log structures that I promised. Whenever you have a morphism x to y and a log structure on y, you can do something that's called pulling back the log structure via f. So this is called f upper star my. How do you do that? It will actually preserve m bar. So you don't touch m bar. M bar is just pulled back as a monoid sheaf by f inverse. So you take f inverse my. What's wrong with that? That's not a log structure. The reason is that the invertible functions get messed up. Yeah, you pull back an invertible function. Well, it has no zeros, but it's a function on y, not an x. So you turn it into a function on x, so to speak, by brute force, by taking a push out with invertible functions on x via the pullback of invertible functions on y. Okay, so there's a kind of diagonal or anti-diagonal action on this, where a function, invertible function on y, maps multiplicatively here and by the inverse here. And that still has an alpha morphism. It's called alpha x to ox by mapping s comma h. S would be a section of f inverse my, so that can be pulled back as a function to get a function f upper star alpha on x. And then, f upper star alpha on s, which is alpha of s pulled back, that's the same, to x, that's a function on x, and then you multiply it by h, which is in ox star. In any case, that gives an abstract way to produce a log structure on x whenever you have one on y. I didn't say this, but the fact is, maybe I should put this in here, that the f upper star my bar is the same as the pullback of mx bar. So it's a kind of minimal log structure that preserves the kind of discrete nature of this thing. So now comes the thing why these kind of log points are natural. You take the inclusion of the zero-dimensional torus orbit, this kind of center point of an affine toric variety, in the affine toric variety, TV sigma. And so this is my f, and you pull back the toric log structure, you get the log point that has this toric modulus q that is given by sigma dual intersected n. Okay, so in particular, let's say we take A1, your q is an n. What you get is a log point that has, for q, that has monoid sheaf n direct sum C star. Let me see how much more I have here. Okay, so this is not so bad. We're not spilling over. Maybe I can even make it today. Are there questions at this point? This may be a place where people start to get lost. So we have the definition of an abstract log structure. Okay, that looks slightly awful, but all the log structures we ever care about will be obtained from a toric log structure by pullback. Okay, so you could think of embedding or mapping your space to a toric variety, and then your sheaf of monads is Mx, looks like the sheaf of monads on the image, but adjusted by the invertible functions a little bit. But of course, this kind of thing this kind of morphisms of logs, this pullback log structure and morphism of log structure is now very important to get flexibility. So we are not oh, here's a question. Say it again. This here. Why is it a direct sum and not a product? Oh, it's a push out, right? So it looks like this. What do you mean? What do you mean? So you mean without this? What does this mean? I see. Okay, so let me try to explain it. So you have a push out diagram of sheaths of monoids. Well, that might not help you, but that's what technically is going on. Or maybe no. Maybe what I should say is the following. Maybe it's easier to just define it. So I kind of said it in words, but you probably missed it. So this is just the pairs S, yeah, maybe I should, yeah, S comma H. So this is in local sections MY. I'm a bit sloppy here. OX cross, okay? No, sorry. What am I doing? Sorry, this is not what I want to write. It's F inverse My, direct sum OX cross, and then you divide out F inverse of OY star, where the action is H times, H is bad, right? Let me call G. Times SH is GS comma G inverse H. Does this help? And this is it is a push out in the category of monoid sheaves. Can you read this? So you would have a diagram. You have a universal property for this diagram. So this is the F inverse alpha morphism, and then you have that guy here, right? Oh, it's hard to write. Maybe I should take the smaller one. F inverse OY star. Okay. Say it again. If this diagram is commutative? No. Oh, if the whole monad is commutative, sure. Yes, it is commutative. I mean, that's kind of suggested by the direct sum notation. But yes. No, sorry, maybe I should have said that. All my monads are commutative, okay? They're submonads of Zn and so on, right? I didn't say this. Yes, commutative monads. We are not that complicated. Okay, so then there's a notion of chart for a log structure that is kind of important. So whenever you have an open subset of X, a chart would be a morphism to a toric variety, together with an isomorphism of your log structure with the pullback log structure from the toric variety. And in algebraic geometry, you would usually do this in the étale topology. Analytically, it's just some open subset. And then a fine log structure, and all my log structures will be fine. I mean, there exist charts locally. And fine saturated, FS, that's one of the few jargons I might use, okay? FS log structures, fine saturated log structures mean You can choose a system of charts such that an atlas, such that the P is saturated. Okay, so then they are always of this form sigma dual intersected M. And then you have an obvious morphism of a log, an obvious notion of a log morphism. It's just what you suggest, right? I would actually, yeah, so you have a scheme X with a log structure Mx, Y, My. Whoops, something is missing here. And so that means you have an underlying morphism of schemes. So that gives you a pullback morphism of sheaves of regular functions. And a commutative diagram like this. So there's this F sharp, that's a schematically pullback of regular functions. And that gets lifted to a pullback that's called F flat. So these are kind of musical homomorphisms. F flat of the sheaf of log structures, F inverse My to Mx. And that is supposed to be commutative. So if you have a map of toroidal pairs, that induces, obviously, a commutative diagram like this. And that's a kind of abstract generalization of this. Then there are morphisms that are kind of boring logarithmically. They're called strict. So a strict morphism is a morphism such that a log morphism, x mx to y my, so that the induced morphism from f upper star my to mx is an isomorphism. So if you want, mx is just a pullback log structure via f. That's a strict morphism. You can check this by just checking it on the discrete parts. The other parts will be taken, all these kind of normal bundles will be taken care of automatically. Okay, so the last concept, I think the last I wanted to explain, I see, and then I want to give one application. And that might spill over to tomorrow's talk. Yeah, we have 3 minutes. Actually, maybe I should stop here. Or maybe I start with the definition and then I'll start here tomorrow again. So a log smooth morphism, this is really why log geometry is useful, I think. It's the notion of a log smooth morphism. So we have learned that working with smooth spaces and smooth morphisms is a lot easier than working with singular spaces and singular things. Log geometry gives you a method to do a lot of the things you're used to for smooth morphisms in a bigger setup, namely in setups where toroidal singularities come up. Anything toroidal looks smooth. There's not much of it's a little bit of a difference, but not much of a difference from a logarithmic perspective. And the definition is a morphism of log schemes is called log smooth if it is kind of locally given by a toric morphism. So this means as follows. Locally on X, you have a diagram like this. I didn't introduce notations U or something, but there's a map X to spec CP that is strict. That means it's a chart, actually. If it's a strict morphism, this means it's a chart, yeah? i.e. a chart. A strict morphism of a toric variety is just a chart. So you have charts for X and Y, and then a toric morphism here. So this means it's given by a homomorphism of monoids Q to P. And whenever you have an X to Y that looks like this is called, at all points locally, it's called log smooth. And anything we will do will have to do with log smooth situations. So log smooth curves or nodal curves, log smooth targets are kind of toroidal geometries or central fibers of toroidal morphisms and these kind of things. Gives a lot of flexibility. Okay, so I think that's a good point to stop. And tomorrow I'll show you how this relates to some classical smoothing theorem of Bob Friedman, his thesis in 1983, smoothing of normal crossings K3 surfaces, and then we move on to tropicalization and so on.